Good afternoon, everyone. I just wanted to take the opportunity to welcome everyone to the Summit 2014. Appreciate you guys being here. My name is Rhys Oxenham. I am a field product manager for Red Hat, focusing specifically on our OpenStack offerings as well as our enterprise virtualization offerings. Today's presentation is entitled An Introduction to Red Hat Enterprise Linux OpenStack Platform. Now, I'm not sure what happened to the technical rating that's listed in all of your forms. It certainly wasn't meant to be a 3. This is definitely an introductory track. So what are we going to talk about in this presentation? Well, I think a common question is, what is OpenStack? Okay, so we're going to try and answer that question in the most sort of basic sense and then build our way up through there. We're going to go through all of the OpenStack architecture, what OpenStack aims to solve, so what use cases it tries to solve. Then we're going to go through actually a live demo. I'm not sure how wise that will be, but we'll soon find out. So let's make a start. So what is OpenStack? Well, OpenStack in its most simple term is what we call a open source cloud operating system. So what do we mean by that? Well, there's a number of individual subcomponents or building blocks that allow you to create an infrastructure as a service cloud platform. Now, OpenStack itself was designed and architected after public cloud infrastructure. Sort of replicates or mimics what you would get from the likes of Amazon Web Services or indeed Google Cloud Platform. Today, OpenStack is led by the vendor-agnostic OpenStack Foundation. These are responsible for the strategic direction of the project and governance of the project as a whole. Red Hat, amongst others, is a platinum founding member of this organization. As I'm sure you can appreciate, there's a huge market momentum behind OpenStack. You can't really read any news articles without OpenStack being mentioned somewhere. There's a whole host of vendors and organizations all building up their technologies based around OpenStack. Why does the world need OpenStack, though? Well, I think we can all agree that cloud is seen as the next generation way of delivering IT to end users, whether that's based on the agility and flexibility it provides to you with things like self-service and pay-as-you-go pricing. But also what we're definitely seeing is that the public clouds like Amazon Web Services, Rackspace, Google Cloud Platform, these are really setting the benchmark on how IT in an ideal world could be delivered to end users. But the problem there is that not many organizations are really ready to start consuming public clouds on the whole. So OpenStack is really trying to target both of those types of issues. First of all, providing you with a self-service public cloud-like platform, but crucially being able to build that type of platform behind your own corporate firewall, within your own data centers. But critically, what we're also seeing is applications are being built differently today, okay? Making use of scale-out technologies and fault-tolerant software. Let's explore that in a little bit more detail. So there are a number of issues with traditional infrastructure. First of all, we're swarming in data. We're drowning in data. We're all producing more music, more videos, more photos and things like that. And most of this data being unstructured proves a great challenge to how we actually process and manage this data. Secondly, the data or the requests for this data are just growing exponentially. Okay? So more phones, more tablets, more laptops, more emerging countries becoming more connected to the internet and things like that. And the bring your own device sort of policy within organizations is making this issue even worse. So when you couple these two issues together and with the crucial fact that applications and the infrastructure that supports these applications was never really written to accommodate the demand that we're seeing nowadays, it of course gives us all great problems, okay? Things like service level agreements, key performance indicators, they're starting to slip or even being missed completely. So what we're seeing is that there's a natural evolution from what we call these traditional workloads, where typically each tier of every application is aligned to a single machine, okay? These tiers don't typically tolerate any downtime, and they rely on underlying technologies like clustering, like the virtualization layer, high availability, to make sure that that application is always up and running in that particular tier. And if you want to accommodate more demand, well, you know what? You have to add more resources to that individual machine, whether that's more virtual CPUs, more memory, more bandwidth, more disk space. So in essence, we're scaling these machines up. So we're seeing this evolution towards what we call cloud-enabled workloads. These are the ones where each tier typically resides across a number of machines, be that 10, 100, or even 1,000 individual machines, all contributing to the SLA of the application as a whole. It's then the application's responsibility to manage its availability and the SLA of the application. It no longer relies on the underlying infrastructure, which means that we can replace some of these technologies like clustering and high availability components within virtualization layers with commodity storage, commodity networks, and commodity compute. So what we're saying here is that instead of scaling up our applications, we're in fact scaling them out. You want to accommodate more capacity, more demand, then you simply add more nodes. So how does OpenStack fit into this type of infrastructure? Well, we see OpenStack as being an interesting platform for lots of different use cases. We speak to a lot of customers in all different sectors, and they're all interested in OpenStack. But what we're seeing is there are actually some sweet spots that we're seeing today. First of all, I mentioned that OpenStack itself is built to be a public cloud-like offering that can be built as a public cloud or indeed a private cloud. So what we're seeing is here we have internal infrastructure on demand. So internal IT organizations, as they're trying to keep up with the benchmark that's being set by public cloud providers and trying to prevent the end users from taking their credit card and taking it directly to Amazon or Rackspace, they can build out a similar platform using the same sort of capabilities in-house. So this is what we mean by some form of private cloud. For developers, if they want to spin up particular environments, they can do this using the same mechanism. So we're just calling this, just called this a sandbox type environment based on sort of self-service. We're also seeing certain organizations wanting to use OpenStack as the basis for their own public cloud infrastructure. So certainly in Europe, what we're seeing is that there's a lot of countries that want to exploit local data regulations where these smaller organizations can guarantee that data will not leave the particular host country. So we're actually seeing there's a lot of interest for actually creating your own public cloud using OpenStack. Finally, we just talked about these cloud-enabled workloads, these scale-up type workloads. OpenStack is, of course, a perfect platform for this. It really hosts the underlying infrastructure for providing these scale-out infrastructure. So we have here web scale applications. So I typically use the example of organizations like Facebook, Google, Netflix, Amazon Prime, those types of organizations that would use web scale type applications where you can pretty much guarantee that the application isn't being served by a single machine. This is being represented by tens, hundreds, or thousands of individual machines. I'm also seeing a lot of interest in the academic or the pharma type use cases, where traditionally they may have used HPC-like environments, but for multi-tenancy and self-service, they're switching over to and looking at OpenStack to provide the infrastructure for that. So let's take a look at the OpenStack architecture. So as I mentioned, OpenStack is comprised of multiple different underlying individual components, individual autonomous components. Each one of these components itself is designed to scale out, just like the applications that it's meant to be hosting. So whether that's for availability, for throughput, or performance, all of these components scale out individually. The crucial thing to understand about OpenStack is that actually OpenStack is more of a framework for how you would implement a cloud. It then relies on plugins and drivers to actually implement your cloud environment with the technologies that you want to choose. OpenStack itself, largely written in Python. In fact, the vast majority of it is written in Python and has a heavy dependency on the underlying Linux operating system. Let's have a look at some of these components individually. Excuse me. So the first one I want to talk to you about today is OpenStack Identity Service, codenamed Keystone. So Keystone is the most important, in my view, the most important component of any OpenStack environment. Its primary responsibility is to be a centralized authentication and authorization store for OpenStack. It maintains a list or a database of users, their roles, and into which project do they belong to. In other words, who's who, what can they do, and to which groups do they belong. OpenStack Keystone provides a catalog of all services. So to use an OpenStack environment, you only ever need to know how to communicate with Keystone. Keystone will then provide you with all of the other API endpoints for all of the other components. It will direct you onto those components. But Keystone is also relied on for validation of an end user's request. So if you wanted to use one of the other components and you wanted to perform a task, perhaps maybe starting a virtual machine on top of your infrastructure as a service based on OpenStack, that individual component would check that what you were trying to do with your request was both authorized and authenticated. Second component is OpenStack Compute, aka Nova. So Nova's primary responsibility is for managing the life cycle of running virtual machines or instances on top of OpenStack and the underlying infrastructure that provides that. In other words, the hypervisors that provide that compute power. Again, being a framework, OpenStack relies on multiple different back-end drivers for communicating with underlying hypervisors. Some examples there being Red Hat Enterprise Linux with KVM, or indeed VMware vSphere as a driver for implementing your compute infrastructure. Next component is OpenStack Image Service, also known as Glance. So when you want to start up a virtual machine or an instance on top of OpenStack, what you typically tend to do is instead of provisioning each virtual machine every time, maybe from Pixie or something like that, you actually build up your virtual machine based on a template or a disk image template of maybe your operating system. Now that can be as basic as a really, really base RHEL 6 install or Windows 2008 install, or it could be operating system, application, and configuration. It's completely down to you as you want to use templates. So Glance itself provides a mechanism for both storing and retrieving disk images as a repository. It supports a wide variety of formats, so your typical ones you might use in a Linux environment, maybe QCOW2 or RAW files, and then you can use things like VMDKs if you already have them, Amazon Machine Images, or industry standard OVF formats. Next component is OpenStack's object store, also known as Swift. So Swift is basically provides a mechanism for both the storage and the retrieval of arbitrary unstructured data, aka objects. So it provides an object interface, not a file or a block-based interface. It's purely for retrieving objects over a RESTful HTTP-based API. Swift itself is a highly fault-tolerable platform, so it takes care of things like replication, self-healing if a node goes offline, and things like that. The object store doesn't actually require any form of storage architecture like a SAN or anything like that. It just uses commodity storage available to a particular node. Next component is OpenStack Networking, also known as Neutron. So Neutron is responsible for providing instances or virtual machines running on OpenStack with access to networks. Okay? So it provides you with an API for defining these networks, what they look like, whether that's IP addresses, MAC addresses, and things like that. But just like all of the other OpenStack components, it relies on plugins for actually implementing the networks based on the technologies that you have available to you within your data centers. So by default, out of the box with OpenStack, the distribution that we ship, we use Open vSwitch. But of course, there's a wide variety of plugins, and I've just listed just a few that came to the top of my head when I was writing this slide deck. The next component is OpenStack's volume service, also known as Cinder. So I mentioned previously about Glance, where you pull or you use it as a mechanism for storing your disk image templates. The default mechanism in OpenStack for providing storage to virtual machines is actually to use the local hypervisor for that disk image. Of course, that perhaps isn't the best way of doing things. Perhaps if you're wanting to store data on that machine and the hypervisor catches fire, you're going to lose all your data, right? So Cinder actually provides you with block storage as a service for your virtual machines. So perhaps you want to attach block storage to your virtual machines for persistence. So you no longer want to use the local hypervisor storage for your data. You can actually back-end out to maybe a SAN or something like Red Hat Storage or something like that. Or indeed, if you want to provide additional storage for your virtual machines, perhaps more than the local hypervisor can accommodate, you simply provision extra or additional storage via Cinder and attach it into your virtual machine. The wide variety of drivers and back-end plugins for use with Cinder, I've listed just as I have done with the other components, some of the primary examples. Next two components, Heat and Ceilometer. These are new ones in the current release of OpenStack. So Heat is all about orchestration. So Heat is all about facilitating the creation of application stacks. Well, what do I mean by an application stack? Well, what you can do with Heat is you can define an entire application, all of the dependencies, maybe that's particular networks, storage devices, particular images that you may want to use, all wrapped up in a Heat definition file, and you can upload that into Heat. Heat will then take care of deploying all of the required resources, all of the dependencies, and it will do things like monitor the application. Perhaps you might want to auto-scale it up or scale it down, or you may want to provide some monitoring to always make sure that the instances it generates are always available. Next component is Ceilometer. So Ceilometer is all about metering and monitoring of your OpenStack environment. So I guess the ultimate goal of Ceilometer is to provide chargeback or billing to your end users within an OpenStack environment. So you can choose what you meter and you bill your customers using Ceilometer on. Perhaps it's CPU time, IOPS, or network bandwidth. It completely depends on what you want to charge on. It's completely extensible. Currently, within Ceilometer, there's a wide variety of meters that are out of the box, but of course, you can write your own based on what you want to charge for within your OpenStack environment. Finally, we have OpenStack Horizon. So Horizon is OpenStack's dashboard. So it basically provides you with a self-service, web-based portal for, as an end user, communicating with OpenStack, and you can do a wide variety of things using it. Maybe it's just starting virtual machines, creating block devices, configuring your networks. You can do it all via this web portal. It is a subset of the capabilities of OpenStack as a whole. It can't do everything, of course, constantly playing catch-up and what makes sense to actually expose within a self-service portal. But there is an admin extension. So to do maybe some of the common administrative tasks like create a user, change a user's password, there is certain functionality exposed by Horizon for doing this. Okay. Let's have a look at Red Hat's involvement in OpenStack. But first of all, the OpenStack community. So the OpenStack community, under the guidance of the OpenStack Foundation, actually releases a new major version or new major release of OpenStack every 6 months. And during this six-month window, there is a lot of development and a lot of innovation, a lot of changes that happen across the code base. The current version that is available today, the most up-to-date version, is codenamed Havana. And the next version, which is actually set to ship later on this week, is called Icehouse on April 17th. Now, the code names are actually based on the locations of where the developer summit happens. So, go into too much detail perhaps at this moment. Havana is apparently somewhere in Oregon. Anyone from Oregon here want to validate that? And Icehouse is actually based on a street name in Hong Kong where the previous development summit was held. So contributions to the project actually come from both corporate and non-corporate entities, the wide variety of organizations contributing to the project, and they're contributing source code, aka trunk code, to the OpenStack project. So if you were to go to openstack.org and you wanted to download the code and check it out, this is pure source code. It's not packaged up for any particular distribution of Linux. Remember, that's a hard requirement for OpenStack. It doesn't provide you with any certification, and support is limited to the open source community. So there's a wide variety of forums and IRC channels, but that's what you're going to get from the OpenStack community. To give you an idea of the current size of the OpenStack community, and this is based on data that's 6 months old from the release of the Havana version back in October of last year. 13,700 plus code commits, 920 individual contributors, whether that's from a corporate background or non-corporate background, 150 plus organizations contributing to the OpenStack project, and 400 plus new features. For the previous statistics on the previous version, some of these were plus 50% over the previous version. So it really is growing exponentially. But if you have a look at Red Hat's involvement specifically, I mean, the first version, codenamed Austin, came out back in October 2010. No points for guessing where they held the first developer summit. That was back in October 2010, and we set our sights on OpenStack and packaging it up for the enterprise quite early on. We started contributing back in July 2011. And we rapidly ramped up the number of engineers and developers we put on the OpenStack project across the past few years' life cycle. So I'll give you an example. In Folsom, we became the #2 corporate contributor. Then Grizzly and Havana were the #1 contributors, so both the previous, the current. And as of today, we are still, because Icehouse is currently still in development, we are still the #1 contributors for that. So we're certainly keeping the record for that. Along the way, we released a number of different distributions based on OpenStack. The first one I wanted to mention was RDO. So I'm going to come on to that in a little bit more information on the next slide. And then after that, we actually released the OpenStack, Red Hat Enterprise Linux OpenStack Platform version 3, which is based on the Grizzly release. And then Red Hat Enterprise Linux OpenStack 4, we launched in December 2013, based on Havana. So how do you go from community source code to an enterprise product? For those of you that are familiar with the way that Red Hat packages up technology based on community editions, taking that through to enterprise releases, it's absolutely no different when it comes to OpenStack. What we have is, as I said, to foster new technology and to build an open source community, we released a community version of our OpenStack distribution that is packaged up by us and the open source community that surrounds this for Red Hat-based Linux distributions, whether that's Red Hat Enterprise Linux, CentOS, Scientific Linux, or even Fedora. You can download packages that are OpenStack packages, the latest sort of versions, with community support, all available at openstack.redhat.com. So what about Red Hat Enterprise Linux OpenStack platform? Well, this is Red Hat's officially supported, enterprise-grade, enterprise-hardened, supported OpenStack distribution. Okay? This is specifically built for, tested, integrated directly with Red Hat Enterprise Linux. It doesn't build on top of any other platform. We still maintain a 6-month release cadence, just like the open source community does with our product. So if organizations want to make use of the latest versions, we will, of course, release a new version of Red Hat Enterprise Linux OpenStack platform based on the latest version that becomes available. However, this comes at 2 months after, or approximately 2 months after the open source community, or the OpenStack community, releases their major version. Why 2 months? Well, we're really focusing with our distribution on making sure that the code that we release is, of course, supportable. And for it to be supportable, it needs to be mature, stable, and secure. So it really is enterprise hardened and integrated directly with the underlying Red Hat Enterprise Linux platform. We, of course, want to work on our ecosystem. One of the big value adds that Red Hat brings is its ecosystem of partners that are certifying their value add components on top of RHEL. Well, we're doing exactly the same thing with OpenStack, whether that's underlying plugins or indeed software that builds on top of OpenStack. We actually extend the life cycle. So whilst there's a new version every 6 months, to relieve some of the pressure on organizations being forced to move or update their entire infrastructure every 6 months, that's not a case with Red Hat Enterprise Linux OpenStack platform. So the current release that we released back in December 2013 has a 2-year life cycle, and we're pleased to announce that we're going to be extending the life cycle of the next release code based on the Havana version for 3 years. Of course, we want to make sure that it's supportable, as I mentioned, and you're going to get enterprise-class support from the OpenStack, or the #1 OpenStack contributors, and of course, based on the reliance on the underlying Linux platform, of course, Red Hat being the leaders in the enterprise Linux space, you're of course in safe hands with that. And during this 2-month life cycle, of course, we're going to be writing product documentation, reference architectures with our third-party vendors. So finally, I'm sure a lot of you are asking yourselves, are you even ready for OpenStack? Are you ready to start adopting these sorts of technologies within your organizations? There may be a few different questions. For example, what do I do if most of my workloads today are traditional? Ones we mentioned typically residing on a single machine and relying on existing infrastructure that's there. Or how do I start adopting cloud-enabled workloads into my infrastructure? How do I manage this and how do I bridge the gap? Well, this is going to be from a high level. I certainly don't want to sound like it's a sales presentation, but Red Hat does have a broad cloud portfolio to assist with this. And we call this Red Hat Cloud Infrastructure. So really quickly, a lot of our customers that we speak to are typically having or have built their traditional sort of enterprise virtualization technologies using the likes of Red Hat Enterprise Virtualization, VMware vSphere, or indeed Hyper-V. And they're extending that technology with perhaps a bolt-on on top, maybe the likes of vCloud. But if they want to start using the scale-out architecture or indeed public cloud infrastructure, there's sometimes a bit of a gap. How do I manage these two environments side by side? How am I going to start adopting these sort of technologies? And so Red Hat is advocating the implementation of an open private cloud or indeed an open hybrid cloud, where using a single unified cloud management platform, consuming both the traditional type of infrastructure and the scale-out infrastructure, you can actually consume both and manage both of these platforms. So Red Hat Cloud Infrastructure with CloudForms on top. Let me repeat that. Red Hat Cloud Infrastructure is a bundle or a product of different technologies that it comprises of. Red Hat CloudForms is the management layer, but it implements Red Hat Enterprise Virtualization for the traditional workloads, Red Hat Enterprise Linux OpenStack platform for your cloud-enabled workloads, but also for customers that are wanting to use OpenStack or make use of other technologies within their environment, CloudForms actually supports additional technologies like VMware and indeed Amazon Web Services. So CloudForms is all about providing you with a single pane of glass self-service portal for abstracting all of these underlying technologies, allowing you to adopt and have an on-ramp to various different technology sets. So if you're interested in how you're going to be adopting cloud-enabled workloads or adopting OpenStack within your existing environments, I strongly suggest you take a look at some of the other presentations and demonstrations on Red Hat Cloud Infrastructure and CloudForms whilst you're here at the summit. Okay, I'm going to attempt to do an OpenStack live demo. As I mentioned, I'm not sure whether this is wise. I have tested this, but you know what it's like in a live demo environment. We'll give it a go. So we're going to use the Horizon dashboard for this demonstration. So this is actually the landing page where you would offer this particular service to your end users, regardless of whether you're creating a private or a public cloud. So I'm going to log in as an unprivileged user. Try that again. All right. So I've now logged on, and the first thing you see when you log on to your OpenStack environment is basically a summary. What's going on in the environment, how many virtual machines am I currently running, what am I consuming? But crucially, as OpenStack is a multi-tenancy platform, you're going to want to introduce some form of quotas or limits to restrict the usage of certain resources within your environment. So you can see at the top, me as an unprivileged user within my tenant, I can use, for example, up to 10 instances, 20 virtual CPUs, et cetera, et cetera. So as I'm not actually running anything at the moment, I'm free to consume at will. There's a number of different tabs on the left-hand side. For example, I can view the instances or the virtual machines that I'm currently running. I can see the volumes, so the block storage devices that I have available to me. I can go in here, I can list all of the different images that I have. Remember, these are the disk templates I have available to me. These are the ones that are available within my project. But as a cloud provider, what you typically do is upload standardized public images that are available to everyone, sort of maybe a corporate standard. So this is where we have this public one. And what I've also done is I've uploaded a RHEL 6 image. So the administrator uploads this and makes it available to all tenants across the platform. There's an access and security tab. And we have something called security groups. So security groups actually allow you to create firewall rules for your instances running on top of an OpenStack environment. And you can set up multiple different groups. Perhaps you have a security group for Linux-based machines, where you'd open up maybe port 22 for secure shell. Or maybe you might have a Windows-based group which would open RDP ports. Or you may want to create security groups based on application profiles. So if you have a particular, maybe it's a database server, you would only configure that particular security group to allow access to to the ports required. We also have another few tabs on the left-hand side, managing the networks. So in here, we can go ahead, we can create networks that are available to the tenants. Now, an important thing to understand here is that we're actually able to create what's called tenant networks within OpenStack. So these are private, abstracted, logical networks that we can create and have full control over. So we can have full control over the IP address ranges, and have full control over whether we want DHCP, DNS, and routing services, all within these virtual networks. So you can see here I've created one called int, as in internal. I've created it with an arbitrary subnet associated to that, and I have full control over that. I can, of course, create additional ones should I need to. All right, so what we should do, let me show you a workflow for actually creating a virtual machine within OpenStack. So we go into the Instances tab. At the top right-hand side, we have this Launch Instance button. So when we want to launch an instance, the first thing it's going to ask us to do, sorry, I probably should have asked, can everyone see this at the back? It's clear enough? Perfect. So it's going to ask you a few different questions. The first thing it's going to ask us for is, which availability zone do you want to provision your virtual machine to? So for those of you that are familiar with the likes of Amazon Web Services and Rackspace, this is actually the exact same concept here. When you are provisioning an OpenStack cloud or an infrastructure as a service cloud, it's common to create multiple different availability zones. These availability zones could represent a collection of hypervisors or indeed an entire data center. So you as an application developer or someone that's going to be deploying your application on top of OpenStack, you're going to want to make sure that you deploy your application split across multiple different availability zones so that your application can sustain the loss of an entire rack or data center, et cetera. You're spreading the load across multiple ones there. As I don't actually have any availability zones available to me apart from the default one, I'm just going to call this is just the default one called Nova. It's going to ask me for a name for my machine. It's going to do Summit 2014. Then we have a flavor. So a flavor represents the amount of resource that this particular virtual machine gets. So on the right-hand side, we have these flavor details. You can see the tiny one represents a single virtual CPU, 20 gigs of disk space, and 512 megabytes of RAM. I'm going to want to create a RHEL 6 one, so I'm going to give it a bit more power. And I've actually created my own flavor that I want to use. So my new flavor actually comprises of 2 virtual CPUs, 20 gigs of disk, and actually a gigabyte of memory. I can choose whether I want one or multiple machines, because remember, the type of platform that you actually, or the type of application you want to upload into an OpenStack environment will be the scale-out ones, where the virtual machines are actually identical. So using this, we could, of course, create multiple within a single command. The next question it's going to ask us is, where do I want to get my boot source from? Do you want to use an image that's being supplied by the Glance repository? Do you want to use a snapshot of one that you've already created? Or do you want to boot directly from a volume? So this is where we can actually boot directly from perhaps a back-end storage array or a software storage platform like Red Hat Storage. So we can bypass the requirements for using the local hypervisor storage. But for this, I'm going to be booting from an image. It then asks me, what type of image do I want to use? It's going to list all of the ones that are available to me in my tenant. So I'm going to just choose this RHEL 6 machine. Next tab is access and security. So this top question here, or top entry box, is key pair. So what's typical across all cloud platforms is that you don't actually ever know the root password to a particular virtual machine. Okay, it makes these images very portable. You don't have to, if you're sending an image or uploading an image, you don't always have to need to know the root password. So what's very common is that the cloud platform will actually inject a public key into the image when it's instantiated. That means that when you connect into this machine, it doesn't require your password, or a passphrase on your machine is of course accepted as well. And then once you're on that virtual machine, you can escalate your privileges and change the root password to something you may want to. If your image supports, there's an agent which you can actually install within your image. If you've installed this agent, you can do a few additional things, like overriding administrative passwords or root passwords directly from the console. So I was going to ask, what security group do I want to implement for this particular virtual machine? Well, as I only have one, it's just going to be the default one, and I'll show you what this represents. Networking. So I only have one network that I've created. This is this internal network, so I'm just going to add that there. If I had multiple ones, I could, of course, add them, and I could change the order that the virtual machine sees them here as well. The final tab is this post-creation. Again, I mentioned the agent that you can implement within your image. If you have that agent running, it's called Cloud Init, for those of you that are interested. If you have this Cloud Init agent that runs within the virtual machine, you can actually inject some code for actually customizing your virtual machine once it gets instantiated. So some of the things you may want to do here, perhaps execute some bash code or some Python Perl code. Or what you can do here is you can use some of the Cloud Init modules, like configuring that machine for Puppet. So when the machine comes up, it may connect out to a Puppet master and then configure itself using that mechanism. But here I'm just going to leave this blank. So final thing to do, if I haven't missed anything out, is hit launch. So what this is now going to do is it's going to find a relevant hypervisor. So Nova, the compute engine, is going to find a relevant hypervisor to start this virtual machine on top of. This is part of the spawning process. As this is actually all running on my laptop, it doesn't have a very difficult decision to make. However, the spawning process is actually going to be pulling that disk image out of Glance and putting it on the local hypervisor. Okay? What you can also do from this environment is you can see, for example, remember this would be a list of all the virtual machines or instances running within the environment. So from this at a glance, you can see all the machines that are running, the current status of that machine, its IP address, which public key has been implemented. You can have multiple public keys, so you want to make sure that you can actually access your machine. And of course, the state, uptime, and there's a menu that actually grows once the machine has actually been started up. So whilst that's running, or trying to spawn up, I'm going to show you something else whilst we're here. So I mentioned the security groups. We can go to the access and security tab, and select the security groups. We can, of course, create security groups or edit ones that are already live. Now, this is dynamic. We can change the security groups once the virtual machine is running. It doesn't have to be restarted or anything like that. This is actually implemented at the hypervisor level. So we can go in here, we can edit the rules. So these are all of the rules that are currently active for my virtual machines that have been assigned the default security group. So you can see we can set based on direction, whether it's outgoing or inbound. We can set this on multiple different protocols, whether that's ICMP, TCP, or UDP. We can set security group rules based on ports or port ranges. And we can also decide on the destination. We can also decide whether we want the firewall rules to be implemented based on a particular inbound source. So, for example, we can add a new rule in here. We can say we only want access on this particular port from, say, a particular CIDR of a network. So you can really restrict things quite nicely here. Let's check that machine is now booting. OK, so this machine is now active. So we can click on this machine and we can find out a few more details about it. We can, of course, view the specs, which we know here, some security group rules, what keys it was used, and whether we have any volumes attached. We haven't created any volumes yet, so this is, of course, going to be blank. But what we can do, we can view the log. So perhaps if your machine isn't reachable on the network, we can actually see the output on the console. Or we can go directly to the console. And this is just going to be a VNC console to the machine. Now, I know this isn't very easy for you guys to see, but you can sort of make out that this is a booted up RHEL 6 virtual machine running on top of OpenStack. So the problem that we have is that this machine is running within this tenant network concept. Okay? It's a private network that all of my virtual machines can communicate back and forth on. But how do I actually connect to that? I chose this 30.0/24 network, but how do I actually connect to that? I can't from my machine. There's no way that I can actually get access to that. So if I was to do, for example, ping 30.0.0.3, well, that's just not going to work. So OpenStack, like Amazon Web Services, has the concept of elastic IPs. So what we can do is we can actually go in here, we can say, I want to associate a floating IP to this machine. So I say associate floating IP address. We can then say I want to add one because I don't have any that have been reserved for me. Then it asks me, well, what pool do I want to consume an IP address from? So as an administrator of an OpenStack environment, you can have multiple external networks. You can allocate or you can provide a certain number of floating IPs to be allocated from. So here I'm just going to choose this external. And for me, this external network actually happens to be my virtualization network that sits on my laptop. So I say I want to allocate this IP address. So it said I've allocated 192.168.122.202 for my tenant. I then associate that IP address to my virtual machine. I only have one running. I say associate, and it says success. That's been associated. So what I should now be able to do, replace that with 192.168.122.202, and now I have access to that. So the interesting thing there is that when you're running application on top of OpenStack, you're going to need to have floating IPs to get actually access to the application that's sitting there. Okay? So the tenant network construct is only one networking implementation. We could spend hours talking about OpenStack networking. You can, of course, bypass the whole concept of floating IPs or the requirement for floating IPs by attaching your machines directly to existing networks in a data center, of course. But this is a neat concept that OpenStack has. All right. So this machine is running. If we go back to the security group rules, what you'll see is that this default one, I can't actually secure shell to this machine. So if I was to do SSH root at that, it's going to sit there. It's not going to work at all. This is based on the security group rules implementation. So if I was working on my application, I figured, it's not working as I expected. What I can do is I can go back and edit these security group rules. Okay? I say edit. I want to add a new rule. This is a particular, there's a wide variety of rules available. For example, secure shell, it knows it's already pre-populated with particular rules. So I'm going to add SSH from a remote CIDR. I'm going to set this to my network on my machine, which is 192.168.122.0, and it's a /24 network. I add that rule, and immediately what I should be able to do, I can connect into that machine directly there. And because it uploaded my public key, note that it didn't ask me for any password. I'm straight onto this machine. And if I look in authorized keys, you see the following SSH key was injected by Nova. So this is my public key from my laptop directly here. Okay, so the next thing I want to just quickly go over, because I'm aware that we're pushing it on time, is volumes. So I can go in here, remember, I'm an unprivileged user here. I maybe want to add additional storage to my virtual machine. Maybe I want to run a particular application that requires more storage than my flavor is allocated to me. I can go in here, I can say I want to create a new volume. First thing it's going to ask, give me a name. So I'm just going to call this volume 1. You can add an optional description, but the type is where this becomes quite interesting. As a cloud provider, I may want to offer multiple tiers of storage to my end users. Maybe I want to have one that's based on Red Hat storage, software storage array, or indeed based on something like IBM XIV or a 3-PAR array. So I can actually configure Cinder, the volume service, to have multiple different backends. So as an end user, I can just choose which one that I want to select here. This is an empty list because I've only got one. But if I did want to offer multiple tiers, I could do it directly here. There may be different costs associated with using various different backends. I can give it a size, so I actually want this to be a 5 GB one. And I can choose what I want my volume source to be. There's two options here. Do I want an empty volume? So this is going to create an empty block device or an empty LUN for me. Or do I want to pre-populate that disk image with the contents of an image placed in glance? The use case here would be, I want to pre-create a volume that I can boot from later rather than using the local hypervisor storage. Well, I want an empty volume, and it's going to create that. So I haven't had to connect out to the storage array to create this LUN. I haven't had to worry about zoning this particular LUN or doing anything like that. This becomes available. I can say I want to edit the attachments, and I can attach this to my instance, the Summit 2014 instance. I attach that directly there. In the background, Cinder and Nova are actually attaching this block device, connecting out to it, whether it's over iSCSI, Fiber Channel, or even something like a libgf API, which we have in Red Hat Storage. And it's going to present that directly to my instance on dev-VDB. So it understands that as a second position. If we go back to my machine, I'll do a D-message there. What you see there, dev-VDB unknown partition table, fdisk-L, we have this, dev-VDB 5,368 megs. That's my 5 GB volume that's been presented to me. So I haven't had to do anything there. I can, of course, do whatever I wanted to on this block device, and it would go away and create it as if it was attached locally. But of course, it's going across the network, or as I said, iSCSI or Fiber Channel. OK, what have I missed? Time-wise, I think I want to use the rest of the time for some questions, should there be any. The only thing I was going to quickly show you was a heat definition file. So I appreciate there's a lot of text here. But whilst what you can use heat for is actually creating these definitions of what your application might look like. This may be a multi-tiered application with database servers, with web servers, application servers, of course. You define it all in here with the resources. So there's a number of different resources, for example, setting up the security groups, allowing port 22 and ICMP, and various other things to create networks. And what we can do in here is we can actually copy and paste all of this code, and we can go directly to the stacks bit at the bottom. We can launch a stack, and it's going to ask us where do we want to get the stack from. Well, I would just want to paste it in, so I can say direct input. I paste this in there. I hit next. And based on the parameters, so if we go back to the template really quickly, there's a number of different parameters which I can override as part of the creation of this stack. It's going to ask me various different questions. So I can go in here, I can say, I want to call this basic definition. I provide my password. I can override particular defaults specified within the file. I just want to upload my public key. Of course, that's the one that's there. I want to use my new flavor. And then I can specify if I want to have external network access, I can do this directly from here. Now, I think I've already got that saved. I launch that. And heat is going to go away. It's going to deploy all of those resources that have been defined within this heat stack definition and manage, create failed. Live demos, right? And manage all of those dependencies for me. So with that in mind, thank you very much for your attention. Were there any questions? Yeah. Mm-hmm. Absolutely. Yeah, so I think the question was, can you automate a lot of this without having to go in via the dashboard? Yes, absolutely. So all of the OpenStack components have an API with CLIs based on that. So you can either communicate directly with the APIs, or you can use some of the CLI tools available. I mean, a quick example I can show you, if I go back to my virtual machine here, I can log in here and I can do, for example, Nova list all tenants, I think it is. And I can list all the virtual machines directly from command line equivalents. So I think it's going to get a little bit loud in here. So I'm going to be here for the next sort of 20, 25 minutes. So feel free to come up if you have any questions. Other than that, thank you very much for your time.